We know the L naught is 2 inches. This is in customary units, so we want to keep that in mind. And we're given the original diameter 0.5 inches. I'll call that D naught for gauge diameter. The applied load is, right, we're applying 10 kips to the top and bottom. I'll call that F so we don't confuse it with the internal load, even though they will be the same. A kip is 10,000 pounds. Yeah. Right, the shear modulus, this is aluminum, 3.8 mega psi, or MSI, so that's 3.8 times 10 to the 6 psi. And then we're given a plot. I'll put that in the given, but we will be able to use that to calculate another property, but we're not directly given what that property is. And we want to know, after we apply this 10 kip load, also based on the experimental information, we want to know the new diameter of the specimen. So we want to find, I'll call it D prime for the loaded diameter of the specimen. Again, a simple free body diagram, but I do want to see it every time. It's only a uniaxial load, so it is obvious that the internal force is also 10,000 pounds. We want to find the new diameter after it's loaded. Where can we start with our given information, and we're given that experimental plot? How can we use this information to get the new diameter? So one way to think about it is go in reverse. So what information would we need to be able to find the new diameter for the specimen? Right, we can get the Young's modulus because we're given basically the point at which the proportional limit is. So we could start there. We know that's what the plot will be useful for. Let's start going backwards. What equation would we be able to use to identify the new diameter of the specimen? So the strain in the unloaded direction will be equal to right, it'll be the change in the right, delta R over R naught, or the change in the diameter over the original diameter. Right, same difference. Since we're given the original diameter, we can start there. 0.5 inches. Right, so that's where we're going to end up. We need to know that unloaded strain, and then we know the relationship is the change in that direction, the change in diameter or change in radius. It'll give us the same ratio over the original diameter in this case. We don't know what D prime is where we need to end up. How can we find the unloaded strain? Or the strain in the unloaded direction?
Find the Poisson ratio and then use
that. The strain in the unloaded direction appears in the Poisson ratio, negative sigma UL over sigma L. I'm sorry, epsilon UL over epsilon L. Do we know the Poisson ratio right now? Or are we given the Poisson ratio? We don't know this yet. We don't know at the moment what this is, but if we find this information, then we can go up here. Right, so we need to find the Poisson ratio. What can we use to find the Poisson ratio? The relationship between those three properties, we're given the shear modulus was the 3.8 million psi. We're looking for nu so that we can use this, but we still don't know what the Young's modulus is. And this goes back to an earlier suggestion, how can we find the Young's modulus based on information that we're provided with? Right, that experimental plot, they tell us the location of the proportional limit, and we know that in this section that we can use the relationship that the stress, normal stress, is the Young's modulus times the normal strain. Based on the experimental plot, that means that the Young's modulus will be the normal stress over the normal strain. So at the proportional limit, 70,000 psi over the normal strain, 0.00614. Tells us that the Young's modulus for this material, 11.4 MSI. That's our Young's modulus. Again, we were given the shear modulus. Now with this relationship, the only thing we don't know, putting that in there, now we can find the Poisson ratio for this material, the aluminum alloy. And that turns out to be pretty high, actually, 0.5, based on this data. We know Poisson ratio. Ultimately, we need the strain in the unloaded direction. If we know that, then we'll be able to find the new diameter, which is ultimately what we need. But what we don't know still is this quantity, the strain in the loaded direction. How can we find the strain in the loaded direction? We can use that, the change in length over the original length. We know the original length for this is 2 inches. We'll need to find what the change in length is. What can we use here to find the change in length? There's a couple of different ways to do it, but think about how we did the last problem. It's uniaxial loading, so what was the formula we could find the deformation? PL over EA is one way we can do this. We found the E. I erased it, but that was, I believe, 11.4 million psi. So that we'll have to use again. We know the internal load is 10,000 pounds. Original length is 2 inches, 11.4 million psi. And the cross-sectional area, we can find, this is, again, I'll reiterate, the area we use here is always based on the original area. We don't compensate for the area shrinking in this calculation. So the gauge or the nominal area was based on 0.5 diameter, 0.5 inch diameter. So to calculate that, it will be pi times 0.5 squared over 4. Deformation will be 0.00894 inches. Which means that the strain in the loaded direction, we'll divide this by 2 inches. The strain in the loaded direction will be 0.00447 inches per inch. With this relationship here, we now know the Poisson ratio. We now know the strain in the loaded direction. So we can use this to find the strain in the unloaded direction or the strain in the radial direction. Strain in the unloaded direction, we have a negative 0.00223 inches per inch. Plugging that back into where we started it all, we ultimately needed to find that new diameter. We know the original diameter. We just found the strain in the unloaded direction was the negative 0.00223 inches per inch. Change in diameter over original diameter. Finally, the only thing we don't know at this point, what's the new diameter? We should expect it to be smaller than it was originally because we have a negative strain. But the new diameter is going to be 0. Again, I'll have 4 digits for this one, 4989 inches.